Homework 21, Hypothesis Test for a Population Proportion, Video 1. In the previous series of videos, we learned how to test if a population mean was equal to a certain value, the null hypothesis, as opposed to its alternative hypothesis saying that the mean was not equal to or greater than or less than that value. We looked at two different approaches. We looked at the critical value approach and the p-value approach. It was a lengthy series of videos, but this series should be relatively short because even though we're looking at a different population parameter, we're looking at population proportion, the flow for each of the approaches, the critical value approach and the p-value approach, are basically identical to the previous videos. The only difference is the context and the formula that you use to calculate the test statistic. So I'll summarize the critical value approach from before. It's exactly the same except for the third step. First step is still state the hypotheses. Second step is still to determine the critical value or values and the critical region or regions. Remember, this is contingent on the significance level, which is the area of the critical regions, and whether or not the alternative hypothesis test dictates a left tail, right tail, or two-tail test. But the third step, to calculate the test statistic, the idea is the same, we just have to modify the formulas. Since we're testing a population proportion, we're going to have a sample proportion as the evidence, in other words, p-hat. So to calculate our test statistic, we're going to take the p-hat that our sample gives us and subtract what we're claiming about the population proportion from the null hypothesis, and then divide that by the standard deviation of the sampling distribution of the p-hats. In other words, divided by sigma sub p-hat. And this formula may look familiar from a previous homework assignment. The only difference is the p's have zeros as subscripts. So the square root of p0 times the quantity 1 minus p0 divided by n, where p0 is the hypothesized value of the population proportion, which can be located in the null hypothesis. But after that, we just compare the test statistic to the critical values. If it lands in the critical region, we reject the null hypothesis, otherwise we don't. And if there's a question to answer, we should answer it. Over here, in an obviously darker font color, because I changed markers, we have an example. A security firm estimates 71.8% of all emails sent is spam. A large company examines n equals 500 emails and discovers 382 of them are spam. Does this provide evidence at alpha equals 2% that more than 71.8% of the company's emails are spam? All right, let's jump right into it. I think I have enough room down here to do everything I need to do. Let's start with the hypotheses. Remember, when you state the hypotheses, it's important to first determine the population parameter you're testing. And in our case, it's either going to be population mean or population proportion. Since we are talking about percents of things having a characteristic, that is a proportion. So the firm estimates that the proportion of emails that are spam is 71.8%. So the firm is contending that P is equal to 0.718. What is our alternative hypothesis? Well, in the question, we're testing that more than 71.8% of the emails are spam. So our alternative would be P is greater than 0.718. Because the alternative has a greater than, that means this is going to be a right tail test. So we should go ahead and sketch our bell curve with the right tail shaded in. And remember, in the critical value approach, the significance level represents the area of the critical regions. That means that this area is 2% as a decimal 0.02. But because we're going to look up a z, we need to append 2 more zeros on that decimal. And so off to the z-chart to track down 0.0200. I invite you to get out your z-chart or get access to one and see if you can find it. If you want to pause the video, I would do that. But I found it, and here we go. If you look in the negative 2.0 row, go across and you'll find 0.0202, and 0.0197. So that's where we're looking. The negative 2.0 row, you'll find 0.0202 and 0.0197. Underneath the, which columns is that? 0.05 and 0.06 columns. Remember, when your area is between two areas in the z-chart, you choose the closer one. Which of these is closer to exactly 2%? By the slimmest of margins, the one on the left, 0.0202. If you subtract 2% from that, you get 0.0002. But if you subtract the other one from 2%, you get 0.0003. So by the slimmest of margins, 0.0202 is closer to 2%. So the z-score that we would use is negative 2.05. Except it's not negative 2.05. Why? It's a right tail. Remember, the areas in the z-chart are left areas. We just looked up a right area. When you do that, the z-score that you look up has the wrong sign. So just keep in mind that if you're on the right, your z is positive. So 2.05 will be our critical value, and our critical region will be the right tail to the right of that. Now that we've set the boundary between rejection and non-rejection, if you're in the critical region, we reject the null hypothesis. Now we have to convert the sample statistic to a z-score as well. Problem though. This is the formula we're about to use. We have everything for the sigma sub p hat. We have the hypothesized value of p from the null hypothesis, 0.718. And we know the sample size, 500. But which piece of this formula are we missing? The p hat. So before we calculate the test statistic, and in general, before you use any formula, you should make sure that you have all the pieces for it. In this case, we need the p hat. And remember, p hat measures the percent of the sample with the characteristic. In this case, the characteristic is an email is spam. So out of the 500 emails in the sample, 382 of them were spam. So if we divide that, sorry, I'm a little premature with the decimal point there. We should get 0.764. I'm pretty sure that's right. I'm not dividing by 2, excuse me. I'm not dividing by 500. I'm multiplying both sides of this fraction by 2. It puts it over 1,000, and I'm pretty sure 382 times 2 is 764. Yeah. All right. So our sample gave us a proportion of 0.764, which is obviously greater than 71.8%, but is it greater than by enough to provide sufficient evidence to reject the null hypothesis? So now that we've got the p hat, we can calculate the rest of the test statistic. The sigma sub p hat is the square root of the fraction. On the top is the hypothesized value of p, so 0.718. Times 1 minus that. Just a reminder, 1 minus 0.718 represents the percent of the emails that are not spam. In the denominator, we have the sample size, which is 500. So all this will go into a calculator. We'll walk over to my camera real quick to make sure I'm not accidentally going off the screen. I try to leave a little bit of a margin. I'm getting close there, but I see how far I can go. All right, so be very careful when putting this in a calculator, and don't forget to do the square root. 0.718 times parentheses 1 minus 0.718, close parentheses divided by 500 equals, and now square root that. I get 0 to 4 decimal places, 0201. So 0.0201. And so our test statistic is going to be z equals what we got from the sample. So 0.0201. No. You see how easy I fell into that trap? I just grabbed the last value I calculated and stuck it there. But that's not what p hat is. P hat is the proportion we got from the sample, which was 0.764. It doesn't matter how good you are. If you're not careful, you will make careless mistakes. Minus the hypothesized value of the proportion from the null hypothesis, which was 0.718, divided by our standard deviation of the sampling distribution of p hat, so 0.0201. Now let's see what this equals. 0.764 minus 0.718 equals, and divide that by 0.0201. And I get to, we'll just take it to 2 decimal places, 2.29. In general, z-scores to 2 decimal places are not a bad idea, especially if you're getting into the z-chart, but that will suffice. So what do we say about the null hypothesis? Do we reject it or not? Well, compare it to the critical value, 2.05, this marker's garbage. 2.29 being greater than 2.05 would fall to the right somewhere, and more importantly, it would fall in the critical region. And when the test statistic goes too far from the middle, we have sufficient evidence to reject the null hypothesis. So does this provide evidence that more than 71.8% of the company's emails are spam? Well, if we're rejecting the null hypothesis, then we're accepting the alternative in its place. Yes, that was strong enough evidence to conclude that more than 71.8% of the company's emails were spam. Hopefully by the time you're watching this video, you've already done some problems in homework 20 and are acclimated to the flow of the critical value approach, and realize that the only difference is the formula that we use to calculate the test statistic. Unlike the formula for testing population mean, in the test statistic, we may need to go get one more value that we weren't given initially, the value of p hat, if we weren't told the percent of a sample, but rather given the ratio of the sample. We'll take a look at one more example using the critical value approach, and then we'll do one using the p-value approach.